I suspected, something about my performance last year helped invite me back, but um, I wasn't, I didn't, it wasn't clear to me it was how ranty I was. So uh, I have a little bit of that, but um, this a little bit closer to normal. This is based on a talk my boss, J.F. Bastian, gave at C++ Now back in the spring. And he ran for a couple hours. Obviously, I'm not going to do that. So this is sort of a tightened up version. And yeah, let's get on with it. So that was a good introduction. I'm with Woven by Toyota. I have a shirt on that says Woven Planet, which was our name as of maybe 4 or 5 months ago. And before that, I think it was uh, I'm not supposed to pronounce it triad, but it sort of is spelled like that. So the kind of big news this last week was starting this past Tuesday, I became the new WG14 convener. So I'm committed to that role for at least 3 years, and I'm already behind in my duties. So that's just awesome. So here's kind of the agenda for today. We're going over safety and security in the languages, the future of the languages, because there's been a lot of consternation and churn, particularly in the C++ community about these things. It kind of came up last night in the panel as well. Jean Heed had answered a question that sort of went to a lot of these concerns. So I'll probably, expand on his responses. So the first one is acknowledge the problem. And so what's been going on that's kind of gotten under people's skin, especially in the C++ community, is a bunch of significant organizations are kind of shitting all over C and C++ these days. And it's not that these people are inconsequential. These are people who can control how much money flows into the community, right? So these are people that we need to pay attention to. And so first there's NSA releasing guidance on how to protect against software memory safety issues, kind of calling out C and C++ for not being memory safe. And NSA is the national security agency in the U.S., but they're mostly part of the Department of Defense. In fact, if you I'm telling secrets on camera. If you run into someone at a conference and they say they work for Department of Defense, they don't. There's no such group as the Department of Defense. They work for the NSA, but they don't want to say that, so they'll say, I work for the Department of Defense. If you actually work for the Department of Defense, you say you work for the OSD, which is the Office of the Secretary of Defense. So there was NSA, and that's sort of, again, a pathway to defense funding and defense projects, right? They could be influential in making those sort of projects inaccessible to C and C++. And, they've done it before. They could do it again. So here's another report on the future of memory safety, challenges and recommendations. This is just an article. The internet has a huge C and C++ problem. Developers don't want to deal with it. Here's a paper from NIST, which is also influential across all branches of the federal government, the U.S. federal government, and probably further afield than that. I mean, I work for Toyota, and I care about these things. And these are all people, I actually know from my days working with the U.S. government. So here's CISA, the sort of the cyber defense agency, secure by design, secure by default. So they go on here about also memory safe languages. And there was also a consumer reports. I thought I included that slide, but this is the This is sort of the group that goes around telling you which car to buy or which washing machine is safe, and somehow they also threw themselves into this, into this argument in sort of a against, memory unsafe languages. So there's always this reaction in the C and C++ community of, well, this is unfair. I've been, people have been trying. People think they've been trying. I've been trying for 20 years to make C a more secure language. I don't think I've had much, if any, success. I tend to think C is probably less secure today than when I started, just because, the preponderance of effort in the committee is to improve the ability to optimize the language. And it's easier to optimize a language if the specification is loose, right? If you have to go from, A to C, and the specification tells you have to stop at B, that sort of limits some opportunity for optimization. So if you can eliminate that immediate requirement to stop at B, that opens opportunities for, faster ways to get to C. But of course, it also reduces the dependability of the language, the predictability of the language, the set of guarantees that you're provided as a developer. And so, there are sort of one extreme of the committee where they don't seem to care if they get the right answer, just that they get the wrong answer quickly. And it seems strange, but for some reason that seems to be the case. So I've been on the C committee for 20 years. This is like the most accurate slide in the deck for me, right? Because every time someone comes to the committee and says, "Oh, there was this huge vulnerability because of C," the response is always the same, which is, "Oh, that's user error," right? And you can always kind of make that argument. There was one inherently insecure function, getS. And somehow we managed to deprecate that from C99 and remove it from C11. So you could still use it, of course, because implementations still support it. But besides that, everything else can be used correctly, right? And it's just a usability issue. Like various functions, stir copy, for example, is prone to misuse. It doesn't mean you can't use it securely. So it's hard to tell people not to use it, and sometimes it makes perfect sense to use it. Yeah, and yeah, I'll save some of this for later. But this is a common response, and after this response, people move on to the next topic, right? They're like, well, that's a user error. That's not something we need to deal with, right? So this is a sort of a way to forego responsibility to make things better, right? Well, that was a user error. Nothing we can do about a user error. Let's talk about how we can make C run faster, right? Which is what everyone seems to want to talk about all the time. So I'm going to talk about ethics. Those of you who know me pretty well realize how weird that is. We were at dinner last night, and there was one extra piece of food, and so I grabbed it. I'm not sure I'm the best person to be talking about ethics, but generally speaking, we want to contribute to society, to human well-being, and acknowledge that everyone's a stakeholder in computing, right? No one's unaffected by stuff we do. In my class that I just finished, I talk about ComAir having a outage at Christmas time because of a integer overflow in their crew scheduling software. There's the Boeing 787 Dreamliner that has a counter that overflows every 248 days. And the fix for that turned out to be let's turn it on and off again every 247 days. That's a true story. They didn't want to actually modify the code. So when you fly on your 787, just hope they rebooted it recently. So, avoid harm, be honest and trustworthy. That's really tough for some folks. Be fair and act not to discriminate. Respect the work required to produce new ideas. Respect privacy, honor confidentiality. So ACM has a code of ethics which, talks about intentional and unintentional harm. Avoiding harm begins with a careful consideration of impacts on those affected by decisions. Overall, the goal is to minimize harm. And I've been teaching I've been teaching secure coding in C and C++ for about 20 years now. And I used to always, ask my classes, like, are they familiar with Star Trek? And then I would tell Star Trek stories. And like people stop being familiar with that. So obviously I've become too old. But I guess Norway, there's some issues. It's not really, at least the original episodes aren't really broadcast here. Not sure where I was going with that. So let me get into a specific example along the lines of things that people are used to hearing me talk about. So let's talk about bounds checking. So, we've all heard of buffer overflows, and we understand that these are not a desired property. It's a form of undefined behavior which, allows an attacker to potentially run arbitrary code on your machine with the privileges of the vulnerable process. So to avoid such a thing, you might want to add a bounds check to your code. So let's say we have a pointer that points to the start of an array. We have a pointer max that points to the end of the array. And we've got a length which is correctly represented as a size t, not as any type of sign type for people who were on the wrong side of my rant last year. So we could test to see if pointer plus length is greater than max. We've got a problem. We're trying to access a pointer that's beyond the bounds of this array. So no matter how you look at this, there's still a bug with this code. And the bug is that for very large values of len, pointer plus len can overflow, and that creates UB. That overflow is not actually signed integer overflow. It's a different type of overflow that's mentioned in a particular section of the standard dealing with pointer arithmetic. So the result is typically wraparound, where you end up pointing to an address that's lower in memory than the original pointer. So an experienced programmer who's become used to this sort of hardware behavior model where you write C source code and it's translated pretty much to the underlying instruction set, might write a check that looks something like this, where they've added an additional clause to the expression here to see if pointer plus len is less than pointer. And this is a way to detect that wraparound has occurred. And it's a bit interesting here that we say the experienced programmer, because if you go to the C Standards Committee and you say, I'm here from Intel and we have a new instruction in our processor that gets better performance, and there's no way to access it, so we need to add something to the standard to support that. You get a pretty good response. People are happy to step up to help you. Now, if you come to the committee and you say, we've noticed that naive programmers are making these same kind of mistakes over and over again. Almost always what you do is you get a yawn. They just don't care about people who don't know what they're doing. It's just, I guess they're struggling with everything else so much that that's just beyond their concern. So if you're trying to convince them of things, right? You might start with a statement like this, where you'll say, experienced programmers such as yourselves are making this type of problem. And then they might like listen, hear you out at least, what your concerns are. So, and this is kind of true. This is the kind of code that an experienced programmer writes, right? You've been around a few years, and you learn that this is, you learn how hardware works. So now the problem is that compilers can eliminate this pointer plus len sub-expression, leaving the entire bounds unchecked. And I'm looking ahead, I'm noticing I don't have the other 5 slides I normally have on this topic, but the problem here is, because that's undefined behavior, the compiler can assume the undefined behavior doesn't occur and remove it. But the specific optimization there is actually algebraic simplification. So you can take a pointer plus an integer compared to a pointer plus another integer and simplify that to a comparison between the two integers. And so this is equivalent to pointer plus len less than pointer plus 0, right? It's the same pointer, so you can algebraically simplify that to len less than 0, right? So len is an unsigned type, clearly can't be less than 0. So that code doesn't do anything and is optimized away. And that's concerning, because frequently code like this code was written by someone at Plan 9 at Bell Labs, right? They're not the worst programmers in the world, right? Those are some pretty smart developers, and they managed to make this mistake, right? So it is true that this is a mistake made by experienced developers. So I worked with a really wonderful human, Chad Doherty, at the CERT Coordination Center. We were both there together, and we developed a vulnerability note on this topic. And in the history of CERT, this was sort of a one-off, right? Because normally they talk about real vulnerabilities in real deployed products, and what we were talking about here wasn't a real vulnerability in a real deployed product. It was a problem with a compiler, which could lead to the introduction of a lot of vulnerabilities, right? So it's a little bit different than what they normally had done. And while we were working on this, we were chatting with GCC developers, and thanks to the internet, those conversations are probably preserved. And you'll find that we were called many bad words, right? We were told, we have the right to do this, and they're right. Yeah, the standard gives you the latitude to do this. David Keaton, who was my predecessor as convener of the C Standards Committee, told me that even when he worked at Cray, and their performance came from strong optimization, that they wouldn't do something like this because it was so error prone. But so GCC has this, and why? So there's a compiler engineer, and I'm going to call him Steely McGeeter, and he works at a really large, successful software company, and they use GCC, and this company has a small number of programs that they run a lot, and so they've got big machine rooms running the same code, and if they can get a 0.5% improvement on their code, they can get rid of 100 machines and save $250,000 a year. So they're motivated to improve the performance of GCC. And so they found this optimization, and they examined their code, and they determined that they would not be affected by this defect, right? So they had nothing to lose, and they had something to gain by improving the performance. And so they really sort of acted in their self-interest in adding this optimization. Now, this is not an optimization, say, that Microsoft Visual Studio would add, right? Because they service a wide community of users, and they don't if they break 1% of their code base, they get 1 million calls the next day, right? So they don't want to talk to people that much. So they don't break the code base like that. But for the GCC community, this kind of thing happens because you've got sort of people making locally optimized decisions that favor their organization, but not necessarily, is advantageous to the entire community. So it gets worse than that. So Steely McGator was actually the friendliest person to us on the dev list, and he said, we said, well, can you reverse this? And he said, well, no, because we really want the optimization, but we can add some diagnostics to inform people that their code is broken. And, we agreed that that was an acceptable solution. So he added a diagnostic to the strict overflow 3 test. So this will warn about cases where comparison is simplified. So for example, x plus 1 greater than 1 simplified to x greater than 0. And at this level of warning, now you can detect when your bounds check is being removed. And it's this is not enabled by default by WAL, so you have to be sort of clever enough to know to add this. So, 10 years pass, 12, 15 years pass. I'm working at Toyota on basically a standard for what sort of options we should use, compiler options we should use. And I throw this in because I've been talking about this for 12, 15 years now. Strict overflow equals 3. And it doesn't really work. And so we start looking at this, and we finally discover that GCC deprecated this in version 8 of their compiler. They haven't updated the documentation, so the documentation still says that this flag is there, but what they've done is they've stopped fixing it, right? So it's still kind of there, it still kind of does something, but if it's broken, they won't fix it. And, so we looked at it, and it was broken. And so we can't use it because we can't deal with the false positives if the flag is not going to be repaired. So we did a little bit more research, and it turned out that not too long after we had this kind of a discussion with Steely, he'd posted, I completely agree with you, the cert issue is bogus, and that this test will have plenty of false positives, but that's not the point. We are defending GCC against an unwarranted attack. The way to defend against an unwarranted attack is to add an optional warning. So this was sort of enlightening to me. I mean, basically, this was a whole deception play by this guy who seemed pretty nice to kind of shut us up and get us to stop complaining about GCC's behavior. I can tell you that I wasn't attacking GCC. I was concerned for their community of developers that, their code was going to have their buffer overflow checks silently removed, and that would have a negative consequence. So this guy, I would say is being overly defensive here, right? He's, and I don't know how. I don't know how many people think like this, he definitely has a very narrow view of who's being harmed and who's being benefited. And, so he's acting in, in support of a very narrow interest while ignoring really the majority of users. So, I added my little ethics quiz. And the funny thing about these slides was I had the actual name and picture of this engineer on my slides, thinking certainly someone in legal is going to tell me to change this. And I got, right up to a couple days ago, and no one had. And so I took the initiative to anonymize it myself because that seemed kind of like risky to me to go put some guy's picture up. But so did this engineer feel like he was being unfairly attacked? I mean, I guess. Behave in an honest and trustworthy manner, give careful consideration of potential impacts on all those affected by his decisions, ensure that all harm is minimized, right? Probably not, right? So those are things that, we need to do better as a community, right? We need to watch out for each other, not watch out for whatever narrow interest this guy was watching out for. So, what can we do? Well, we could get better at our jobs, or we can bring in the right type of expertise. So one approach, right now there's not a lot of expert participation in standardization committees. There's no one from NSA, there's no one from NIST, and these people are consequently publishing, kind of negative articles about C and C++. Probably if we brought them in and involved them in the process, right, they would feel more engaged. Maybe they can make a difference, and maybe that would have some positive outcomes. The other thing we could do is develop these skills, learn more about secure coding and safety and so forth. The next thing we could do is quantify the threat landscape. So there's a variety of adversaries, and you should consider who your adversaries are. If your adversaries are nation states, then you have to be really good. I think my joke was kind of, so there's organized crime, coffee shop criminals, loved ones, and script kiddies. It's always nice to put your family in the list of adversaries that you have. And then there's just, white hat hackers. But, if your enemy is coffee shop criminals, for example, you might be okay, erasing your disk or something like that. But if your adversary is a nation state, you probably want to erase your disk, burn the disk, take the ashes from that and make sure you scatter it widely across the Pacific Ocean. That will probably keep you safe from nation states. But, there are adversaries who can, put your data under an electron microscope, right? So those are tough adversaries. So you sort of have to figure out who your adversaries are and what you need to defend against. Set priorities. What are the prevalence of different types of exploits? What techniques are available to prevent these exploits? What's the cost to implement these for organizations to deploy these? How are the different techniques adopted? And how does each technique affect the exploit classes? Do we completely eliminate a large class of exploits? That's great. So Microsoft did a root cause of CVEs in 2018. Stack corruption's there, heap corruption. Stack corruption actually is a pretty small sliver there. That's something that people talked about a lot, and maybe that's had sufficient focus to sort of close that slice up. Heap corruption, use after freeze, very big, type confusion, uninitialized stack, heap out of bounds read, and of course the largest category of all, other, right? And so it's it's a challenge. There's a variety of problems, and solutions for C are not the same as C++. They're not the same issues for Java or some other language. So increasingly we've sort of balkanized in the languages that we use. I kind of see that as a trend that's likely to continue. So there's a lot of work to be done to sort of tie down all these languages. So understand user impact. This is an interesting couple of slides. I mean, so in my lifetime, well, maybe not all of these in my lifetime. No, definitely not all these in my lifetime. I'm old, but I'm not this old. So Challenger disaster, I clearly remember. 3 Mile Island is in Pennsylvania, my home state. But that was on TV when I was young. Chernobyl, excellent miniseries. And if you watch that, it's got all the classic kind kind of failure scenarios of management refusing to acknowledge the problem and, the engineers kind of pulling their hair out, literally pulling their hair out. Is that a bad taste joke? Tacoma Narrows Bridge, I think that was before my time, but you've probably all seen the videos of the bridge that was oscillating with the wavelength of the wind through the canyon. Hindenburg disaster, Johnstown flood, that's again a Pennsylvania, something that happened locally in Pennsylvania. Apollo 13, also a great movie with Tom Hanks. But the thing about all these disasters were engineers looked at each of these, studied these, right? You still study Tacoma Narrows Bridge in engineering school. And they said, how do we prevent this from happening again? And for the most part, these problems have been addressed, right? They've come up with solutions, and we haven't burnt any more astronauts to death on the launching pad. So we've learned from these mistakes, and we've improved the safety and security of these systems that we rely on. Now, software is not really the same thing, right? We have the Morris worm from 1988. That was the event that caused the creation of CERT, which is where I worked for many years and kind of got my start in software security. That was a buffer overflow. Clearly now buffer overflows are not an issue anymore, right? It's been, but yeah, of course they are. So somehow we didn't learn from that. I used to cover the Ariane 5 rocket in my class at CMU, and that was written in Ada, which kind of proves that it's not just C and C++ that can be problematic. And they had they had a variety of interesting failures. One of which was floating point to integer conversion error, which was the precise technical reason that triggered the explosion of that rocket. But we still have exactly those problems. Nothing's been done to change that. Theric 25, that was almost 40 years ago. We still have data races. The NASA Mars Climate Orbiter, where they got the units confused. No one's done anything to fix that problem. Bitcoin, there's all sorts of kind of problems with Bitcoin. There's a new wraparound vulnerability in Bitcoin, every couple of months it seems. Heartbleed, the go-to fail, Y2K, all these problems that the software community's managed not to learn anything from, right? We just kind of went, oops, and just ignored it and kind of went on. And so, we we call ourselves software engineers, some of us, but it's not clear that we deserve that title. Engineers learn from their mistakes. I don't know if software engineers have. They tend to just ignore it and move on full stream. So moving on to functional safety. I've done security work for years. That's still of interest to Toyota, but probably on top of that is functional safety, right? We don't want people to get harmed while driving our vehicles. So functional safety is systematic processes used to ensure that failure doesn't occur. And so there's in functional safety, there's a progression of definitions. So there's a fault, which is just a passive flaw, right? Something that's a bit wrong in your code, but doesn't necessarily have any consequences, might not even result in an error, right? You could have a wraparound, a possible wraparound, but maybe it's not triggered, so it doesn't really result in any problems. So when a fault causes the program to have an unintended outcome, that's referred to as an error. And at the end of the is the failure, which is when you have a functional unit that's no longer able to perform its function because some sort of fault has led to an error, which has led to failure of a subsystem, and having your braking system fail, or your steering system fail, right? That's can have safety consequences, obviously. So this is what Toyota and safety critical organizations mean by safety, right? Functional safety. It's quite different when you go to a C++ meeting and people are just all over the place, right? So what you get a lot is, well, safety means obviously type safety, right? So if we have type safety, we don't need to worry about anything else. Or safety is memory safety, right? So you'll get that from many of those articles I cited at the beginning of the talk, NSA and NIST and so forth. Or maybe the safety is thread safety. So these are all sort of prerequisites. These all lead to basically correctness of your code, but correctness is not the same thing as safety. So type, memory, thread safety don't ensure program correctness. They basically bound the possible behaviors, right? So you can, you have the ability to analyze the potential behaviors of your program, right? So if you have undefined behavior in your code, right, that code can then do anything. And so you can't analyze the possible behaviors because it's infinite, right? It could be anything. So, eliminating undefined behaviors is basically a prerequisite to being able to analyze the code for correctness and safety. So of the CNC undefined behaviors, some can clearly be security issues. It's important that safety, shouldn't be compromised through a single failure, because that's really difficult to prevent. So this is a rough relationship of these things, and it's not entirely accurate, but functional safety depends on security, right? If you're driving down the road and someone hacks your car through your Wi-Fi system and locks your brakes up, that's a safety issue, right? Clearly. There are security problems that are outside of safety. So if some hacker gets into your car and steals your credit card information that you've installed so you can, purchase songs or whatever from your vehicle, that's a security issue. It's not really a functional safety, right? That's not going to harm anyone except, in their wallet, I guess. And type safety, memory safety, thread safety, these are all just kind of pillars upon which security, which are necessary to achieve security and consequently functional safety. There's a little bit of a somber audience. I mean, I guess this is kind of a downer talk in a way, right? You kind of get up and shit on everyone for an hour, and then catch a flight back to Pittsburgh. I'm not meaning to do that, right? My goal is I would like us all to do better, right? I'd like to see, C and C++ succeed and continue to be used, and be able to develop systems safely and securely with these languages. Toyota has another idea called Poka-yoke, and this is to provide mechanisms to avoid unexpected surprises, right? And this is kind of the idea that people are idiots, but they're ingenious idiots, right? And they always seem to circumvent whatever protections you put in place. An example of this is seatbelts, right? You put seatbelts into cars to keep people safe, and they forget to put them on. And so, we try to put a layer of protection, right? We put an annoying beeping noise, right? And, my son, he's a young man, so he's clearly immortal. Nothing, he can never die or come to harm. And so sometimes what makes him put a seatbelt is, he's just annoyed by the beeping and wants to make it stop. I mean, so that's what drives his behavior more than the concern for his, existence. So this is a concept to try to foolproof things, try to give people diagnostics, try to give people, runtime solutions that will catch, coding errors before some critical undefined behavior occurs. Oh, and that kind of reminds me, back in I'm going to say C11, Dr. Tom Plum and I wrote Annex L, analyzability, for the C standard. And it basically went through and it enumerated 9 or 10 undefined behaviors and said those can stay the same, but all the other undefined behaviors are going to be recategorized as what we call bounded undefined behaviors. And what this meant was that there were certain things that these bounded undefined behaviors couldn't do. So, of the, say, 205 undefined behaviors in C, right, this got, this turned 195 of them into bounded undefined behaviors. And the specific thing that we wanted these bounded undefined behaviors not to be able to do was to write outside the bounds of an object. And it wasn't hard, it wasn't easy to get that annex introduced. We went back and forth with all the members of the committee and all the implementations, and we all got them to agree that those 9 or 10 things were all, the only undefined behaviors that could cause a write outside the bounds of an object. So that was, again, C11. It's now 2023. And 0 compiler implementers have implemented Annex L, right? No one has done that. That's a nice Poka-yoke, right? I mean, you're limiting the harm that these UBs can cause. And everyone kind of agreed these were a reasonable list of things to do. The one guy that was going to do it was Doug. Doug, I can't even remember his last name. He worked for Sun, and then he worked for Oracle. He started on this, but retired before it was completed, and no one took on the work after that. So, fine idea, no real follow through on it. So when you look into mitigation, one of the things to consider is how difficult it is to apply that. So if you have a mitigation where you don't have to recompile the software, update the operating system or something like that, and you get the security improvement, that's clearly the easiest for people to adopt. The next easiest is don't change the code, just recompile, and you'll get this improvement. Next is there's some small code changes, or maybe there's some significant code changes. So it's not that, all of the things could very well make sense, but it's an element of, how broadly your improvement will be adopted. So safety and security frequently trade off with other quality attributes. Sometimes I talk with intelligent people who don't believe in trade-offs, but I think that flies in the face of reality. I mean, you see trade-off decisions made all the time. And so whenever there is a trade-off between performance and security, C and C++ always select performance. I teach that in my class. I have this longish story about Microsoft Visual Studio deploying type-checked STLs and how the community basically chewed that up and spit it out because it introduced some overheads. And so, we've kind of learned, some of us kind of learned, if you want, security solutions to get adopted, they have to have a neutral effect on performance or possibly improve performance, and then you can get them to stay. But anything that introduces a performance overhead really gets rejected by the community, and that's that Microsoft example is a compelling example of that. So an interesting trade-off between correctness and security. J.F. Bastian, my boss at Toyota, Woven by Toyota, he has a proposal for automatic zero initialization stack variables to eliminate, the undefined behavior of reading uninitialized variables. And so, say you do initialize everything to 0. So Unix permissions uses 0 to mean root, right? So if there was a uninitialized, UID, and now this change were to initialize that to 0, that could be, that's obviously the worst possible default in that case for security, right? So there's an interesting little trade-off, what does make sense in that situation. So what do we need to do? We need to work with others beyond the language. I don't have any kind of countdown clock, but I think I go for another 10 minutes, right, to 10. So, we can make improvements in computer hardware to help security and safety. Operating systems training. I'm a big advocate of training, mostly because I deliver training. But it's half the equation, right? Half the equation is making better tools, and the other half of the equation is making smarter developers. Better analysis, better tools, various other standards. There's always a chance that people will come in, governments will come in and start to regulate things. I have that picture of Ada there on the left for that reason, right? I mean, some of us are old enough to remember the U.S. government mandating Ada back in the 80s, and that didn't really particularly work out well. So you could see this, you can kind of feel the currents and think that this is something that might be in the future, right? If we don't, as an industry, sort of auto correct ourselves. So what the government's done before is they've done things like said, well, if you're writing software for us, you have to use a memory safe language, right? And they'll give you a list of ones they think are or aren't. Again, this is the sort of thing they've done before with Ada, so you have to believe they could do it again. I've been around for a while now. I don't remember in my lifetime having a more stupid government than we have today. I mean, these folks are morons. So they could do anything. I mean, this wouldn't be the dumbest thing they've done, this week. Sorry, wrong direction. So again, it's not theoretical. There are kind of things floating out there, right? So if someone decides to enact these, there are existing plans that are floating around. Okay, so let's look at some other languages. And John He does a really good job of this because he's a first. Are you out there? I think you are. I'm going to pretend like he is because we're great friends and there's no way he would skip my keynote talk. So he's quite good at this because he's got some strong knowledge of a variety of languages beyond C and C++. So C and C++, are different languages and have different philosophies in some ways. So C, in our charter, it says that we only want to provide a single way to perform any given operation. And so we also refer to that as conservation of mechanism. But the downside is we can't get rid of anything, right? Because kind of the first rule in C is the world runs on C, and we don't want to break the world, right? So we don't want to do anything to break existing code that really, that's a very high bar for us to consider, ignoring that rule. So C++ is a multi-paradigm language. Presumably there's a safe subset that you can and should use, but no one knows what it is. Or at least no one, you can't find two people to agree on what it is. So the next step, maybe you could rewrite your code in some other language. Rust and Swift, have nice safety properties. My experience over time is that rewriting code is not something that's typically funded, because management looks at that and says, what new features will this produce that we can, get new clients and sell more products? And, the answer is there's no new features, we're just rewriting it. Then management is confused as to why you want their money. So this can be difficult to rewrite code. Rewrite it in Rust. To date, there have been 0 memory safety vulnerabilities in Android Rust code, so there are some positive properties to that. What do you use for new code? There's this lovely quote from Greg Parker, programming is impossible. Rust simply enforces that at compile time. Which is, C programming has this interesting property that most C programmers acknowledge, which is, the compiler is something you have to just get past to get to the actual work of coding, which is debugging. And it's quite possibly not a good philosophy. It's more cost effective to let the compiler find your problems. People, famously in my line of work, like to shut off the signed, unsigned comparison flag. As a code auditor, first thing I do is I turn that back on, and I am already rich in findings, right? So I've already found more problems than I'm going to be able to type into the report in 2 weeks. So what's the future hold? C and C++ aren't going anywhere, right? I still have clients, or I had clients in the Air Force using COBOL, and we cannot get those folks off of COBOL. It's not that everyone isn't trying; it's just a hugely difficult problem. C and C++ have their uses. Last night, someone asked us on the panel, why would you start a new project in C? And I think I said something weird like, C is a sharp knife for dangerous children, which got a laugh last night too. But it is a sharp tool for people who don't want the language to get in the way of what they want to do, right? So there are uses for these languages. So this is where quite possibly my opinion diverges from my boss, JF. There's a lot of consternation in the C++ community about all these reports that have come out. The C community, on the other hand, has just yawned about it. Like, it's nothing new to them. They've been called worse things, and they just brush it off and continue doing what they're doing. So C, I think C is right. They know who they are, and they're not going to change. It is what it is. C++, on the other hand, is kind of running around with the hair on fire. There are a bunch of people heading for the exits. There's a ton of successor languages now, like Carbon and Swift maybe. I forget all the names of all the successor languages, but at C++ now, this C++ conference, 2/3 of the talk were on successor languages. Like, I was having a hard time going to a talk on C++ at C++ now. So it does feel like a lot of people are running for the exits. And then the people who are around or who are remaining seem kind of disillusioned. What's the word? Disillusional? Yeah, disillusional. Okay. So they're kind of sitting there saying, well, how do we make C++ a type-safe language? How do we make it a memory-safe language? How do we make it a thread-safe language? And I'm really certain the answer is that you just can't, right? Because so you can add features which are type-safe or memory-safe, but the problem is how do you eliminate features that are not memory-safe, right? And you can't do that without breaking a lot of existing code, maybe becoming a language that isn't C++ anymore. How do you eliminate completely pointer arithmetic? How do you turn that off? And when NIST or NSA does an assessment of C or C++, the question they're going to answer is, can developers write memory unsafe code in these languages? And the answer, I think, is always going to be yes, if you can't eliminate these legacy features, which I don't imagine you can eliminate. So, we can improve the safety and security of these languages, and we should. And those improvements will hopefully extend the shelf life of these languages. I don't really believe that languages are meant to be forever. There's kind of there's a cycle, right? You have a period where you can you can look at past mistakes. You can design a new language that learns from those past mistakes. You can you have a period where you can fix your own mistakes, right? And then suddenly comes a day when you try to fix one of your mistakes, and the community says, no, we can't afford to update all the code we've already written in your language, so that stays. And now your days are numbered, right? Eventually, you're going to get basically destroyed by your own success. But that's okay, because we're going to have successor languages, we're going to have children. They're going to go on from where we left off and do a better job. So that's my talk, and I think I'm ending on time. So thank you very much.